Next, techniques for reengineering. Software engineering uses several automated analysis techniques to understand or improve or transform the existing software systems. Since the important design information is often missing from the legacy systems, developers rely on analysis techniques to recover that hidden knowledge from the source code. One important technique is the lexical analysis. This is the first phase of the compiler, and it is also called scanning. So in this phase, the source code is broken into small meaningful units called tokens. A token is simply a sequence of characters treated as a single unit in programming language. For example, keywords like if, return, and while, identifiers such as variable names, or numbers or operators. If we write this statement as if x is greater than 10, the lexical analyzer converts this into tokens: if keyword, then starting bracket, id, greater than sign, number, and closing bracket. So these are the tokens that are then passed to the next stage, that is called syntax analysis. Syntax analysis is also called parsing, that checks whether the sequence of tokens follows the grammatical rules of the programming language. For example, if the brackets are missing or statements are incorrectly structured, the parser detects that syntax errors. The parser also creates a structure called a parse tree, which represents the organization of the program. This figure demonstrates how a compiler analyzes, understands a program statement using lexical analysis and syntax analysis. At the top, we have the example statement. The first step is lexical analysis, shown on the left side of the figure. So here the source code is broken into small meaningful units called tokens. For example, in that case, a result A, B, and C are identified as identifiers. Equal is recognized as an assignment operator. Plus and asterisk are arithmetic operators, and semicolon is recognized as punctuation. So this tokenization process helps the compiler understand the individual components of the statement. Below that, the figure shows simplified grammar rules used during syntax analysis. These grammar rules define how valid statements are formed in the programming language. For instance, a statement consists of an identifier followed by an assignment operator, an expression, and a semicolon. Expression can contain terms connected by operators like plus, and terms can contain multiplication operations. So using these grammar rules, the parser constructs the parse tree shown on the right side. The parse tree represents the hierarchical structure of the statement. At the top is the complete statement node. This is divided into components such as the identifier result, the assignment operator, and the expression on the right side. The tree further breaks the expression into smaller parts. An important observation here is that B into C is grouped together under the multiplication operation before being added to A. This shows operator precedence, that is, multiplication happens first, addition happens next, and the final result is then assigned to result identifier. So the parse tree visually explains how the compiler interprets and organizes the statement internally before the execution or code generation. After syntax analysis comes the semantic analysis. So this phase determines the actual meaning of the instructions and statements. Semantic analysis is the phase of program analysis that focuses on understanding the meaning and logical correctness of the program statements beyond just the syntax. The first role of semantic analysis is to determine the meaning of instructions. Even if a statement is syntactically correct, the compiler must understand what the instruction is intended to do. Another important role is to analyze the behavior of the statements. Semantic analysis studies how instructions behave during the execution. For example, if we have a statement like age is greater than 18, here semantic analysis understands that this condition controls the decision-making behavior, while the execution depends on whether the condition is true or false. It also helps to identify how loops, conditions, and functions calls affect the program flow. Semantic analysis also checks the logical correctness. A statement may follow grammar rules perfectly but still be logically invalid. For example, consider the set of statements like int x and then x is equals to hello. So this statement is syntactically correct, but the semantically incorrect because a string value is assigned to an integer variable. So this statement is syntactically correct because the semicolon is present, the assignment operator is properly used, and the statement structure follows the C language grammar rules. So the parser accepts it as a valid statement structure. However, it is semantically incorrect because x is an integer variable and hello is a string. So assigning a string to an integer doesn't make logical sense. So this error is detected during semantic analysis, not syntax analysis. Another role is to study the relationship between the instructions. Program contain many dependent statements, and semantic analysis examines how they interact with each other. Finally, semantic analysis helps us to understand the overall program functionality by analyzing the meanings, relationships, and behaviors. Developers and tools gain a deeper understanding of how the software actually works. For example, in a banking application, semantic analysis can help to identify which instructions are related to bank, maybe balance updates, transaction validation, or maybe account verification. So, overall, it moves beyond simply checking the grammar, it focuses on understanding the true behavior and logic of the software system. In simple terms, syntax analysis checks the structure and semantic analysis checks the meaning. Together, lexical, syntax, and semantic analysis helps the developers to understand the internal structure and behavior of the software systems. Semantic analysis determines which variables depend on other variables, how data moves through the program, and how the instructions are logically connected. For example, a semantic analysis identifies that salary is equals to basic plus bonus minus tax. So it depends on the value of basic, bonus, and tax variables. So this dependency information is essential for program slicing. Program slicing is a software analysis technique used to isolate only the relevant parts of the program related to a particular variable, computation, or functionality. In large software systems, developers often do not need to study the entire code base. Instead, they may only want to understand how a specific value is calculated or how a particular feature works. Program slicing helps by extracting only the statements that directly or indirectly affect that functionality. For example, consider a payroll system where the developers want to understand how the final salary is computed. Instead of analyzing thousands of lines of unrelated code, program slicing identifies only the statements connected to salary calculation, such as tax deductions, bonuses, overtime calculation, and employee allowances. So this greatly reduces the analysis complexity and helps the developers to focus only on the important parts of the system. Program slicing is especially useful in debugging, reverse engineering, maintenance, and program comprehension because it allows the engineers to quickly locate the relevant code sections without being distracted by unrelated parts of the program. So program slicing improves efficiency by narrowing the analysis to only the code that matters for the particular task or behavior. Another important concept in reverse engineering is the use of decompiler. A decompiler is a tool that is used to translate the compiled machine code back to a high-level programming language such as C or Java. It is especially important in situations where the original source code is not available. Normally, a compiler converts the source code into executable machine code. So, decompiler attempts to reverse this process. So, first, the recompilers are used in reverse engineering. So, reverse engineering means analyzing a finished software program to understand how it works internally. For example, imagine you have a mobile app file but no source code. A decompiler can help to convert the app's binary code back into a readable form so you can study its logic, like how login authentication is handled or how data is processed. So this is commonly used in cyber security research, malware analysis, or software compatibility studies. Second, decompilers helps us to recover the lost source code. Sometimes the developer loses the access to the original source code due to hardware failure or missing backups or outdated systems. In such cases, if the compiled program is still available, a decompiler can reconstruct a version of the original code. For instance, if a company builds a legacy software system years ago but they lost the project files, so decompiling the executable might help them to retrieve a readable version of the code to continue maintenance or updates. Third, the compilers assist in understanding binaries. Binary files are not readable by humans because they consist of machine level instructions. Decompilers translate these into a more understandable structure. For example, instead of seeing the raw binary data, a developer might see a reconstructed function like calculate total price with the loops and conditions. So this makes it easier to analyze how a program behaves, debug the issues, or verify what a program is actually doing behind the scenes. Once the system is understood, restructuring may be performed. Restructuring means transforming software into a better internal form, preserving its external behavior and functionality. For example, old go-to statements may be removed and replaced with a structured loop and functions. Similarly, modules may be redesigned to ensure better modularity with a single entry and exit points. Before we compare restructuring and refactoring, it is important to understand a common idea that connects both of them. In software engineering, there are techniques used to improve the existing code without changing what the program actually does. The goal is not to add new features or alter the functionality, but to make the code better in terms of structure, clarity, and maintainability. Two important approaches used for this purpose are restructuring and refactoring. While they sound similar and often used together, they operate at different levels of, change and scope within a program. They both mean improving the code without changing what it does, but they are used in slightly different contexts. So refactoring usually refers to improving the internal structure of the source code while keeping its behavior same, and this happens at the code level. It is done by developers while maintaining the source code, and the focus is on readability, maybe removing the duplication, improving the design, and improving the maintainability. Restructuring has a more broader term, so it is more general term that includes refactoring but also bigger changes to the structure of the program. So it can involve large scale changes, and it may include reorganizing the modules, architecture, or even the control flow. So it is used in software maintenance, or modernization. For example, splitting a large monolithic program into multiple modules or services, or changing file structure or program architecture while keeping the functionality same. So refactoring involves small and safe code improvements, while restructuring involves larger structural changes that may include refactoring. Now let's look at software engineering from process and data improvement techniques perspective. Software reengineering is the process of analyzing and modifying existing systems to improve their structure, as we clearly discussed before. So it focuses on understanding the existing system and transforming it into a better version through systematic improvement. So it involves two aspects: the process reengineering and data reengineering. Process reengineering focuses on improving the internal logic and control flow of the program. Inefficient or poorly structured code is redesigned into a cleaner and more maintainable forms. For example, duplicated code can be consolidated into a reusable functions, making the program easier to manage and understand. Data reengineering focuses on improving how data is organized, stored, and used within the system. This may include removing the redundant data, restructuring the databases, or replacing hard-coded values with configurable data sources. For instance, instead of embedding tax rates directly in code, they can be stored in a database table, so they can be updated without modifying a program. So we are just done with the techniques. Together, these techniques helps us to organize and understand the legacy systems and recover the lost information and improve or modernize the software effectively. Now let's have a short quiz. So the first scenario says, what is the primary purpose of lexical analysis in software reengineering? Maybe to check logical correctness of a program, to convert machine code into high-level code, to break the source code into tokens, or to analyze the program execution flow. So the correct answer is to break the source code into tokens. So lexical analysis, as we discussed, is the first phase of program understanding. So in this stage, the compiler scans the source code and breaks it into meaningful units that are called tokens. Next, which phase detects semantic errors like assigning a string to an integer? So if you recall, we discussed that during semantic analysis. So even if a program follows correct grammar rules, it may still be logically incorrect. So it ensures that the program, semantic analysis shows that the program makes real world sense, not just grammatical sense. So the answer is semantic analysis. What does program slicing primarily do? Here are the options. So the correct answer is C, that it extracts only relevant code related to a variable or a function. Program slicing is like zooming into a specific parts of a large system. Instead of analyzing thousands of lines, it isolates only the code that affects a specific computation. So slicing is focused code extraction technique. What is the main difference between refactoring and restructuring? Here are the options. Correct answer is C, that is refactoring is a small code level improvement and restructuring is a large structural change. So they both improve the software without changing functionality, but the scope differs. Refactoring is focused on small changes and restructuring is focused on large scale changes. What is the primary role of a decompiler? Here are the options again. Correct answer is C. A decompiler performs the reverse process of a compiler, that is high level code to machine code to high level representation. So it is used when the source code is lost and you try to study the binary or studying the malware. So it helps the developers to understand what a program is doing internally by converting the unreadable binary into a readable source code structure. Now consider this scenario. A company has an old banking system written decades ago. A system is hard to maintain and developers do not fully understand its structure. The company wants to understand how transactions work, recover the missing design knowledge, and improve the system structure without changing the functionality. So they use decompilers, program slicing, and restructuring. So just take a pause and think how these techniques helped in solving the problem. The company uses decompiler to convert machine code into readable high level code. So this helps them to understand how the banking system works internally, even the original source code is lost. Next, they apply program slicing to focus only on transaction related logic. Instead of analyzing the entire system, they isolate only relevant parts of it like account balance updates, withdrawal, deposits. So this reduces the complexity and helps engineers to focus on critical functionality. Finally, they apply restructuring, where the system is reorganized into a cleaner design. Poorly structured logic is improved, modules are separated, and the code is made more maintainable without changing the actual behavior. Overall, these techniques helps in recovering the lost information, simplifying the understanding, improving the maintainability, and modernizing the legacy systems.